Okay, so let's define a p-series. A p-series is a series of the form the sum from n equals 1 to infinity of 1 over n to the p, where p is a positive real number. So it turns out that if I have a series of this form, it is pretty easy to determine whether this infinite series converges or diverges using the p-series test. So the p-series test says that if we have a p-series, the sum from n equals 1 to infinity of 1 over n to the p, that it converges if and only if p is a value strictly greater than 1. So another way to say that is if I have the sum from n equals 1 to infinity of 1 over n to the p, this thing converges if p is strictly greater than 1, and it diverges if p falls between 0 and 1 including 1. So that part we kind of already know. If p equals 1, then we actually have a special series that we know by name. So if I have 1 over n to the 1 right here, from n equals 1 to infinity, well then we know this to be the harmonic series, which we know diverges. So we're including, if we have any other number less than 1 for this exponent, that the p-series is also going to diverge. So only if p is greater than 1 is this type of infinite series going to converge. Okay, now let's take a look at some examples. We want to determine whether the following series converge or diverge. So I have the sum from n equals 1 to infinity of 1 over the square root of n. So I'll go ahead and show one additional step of work, which is to rewrite a square root as n to the power of 1 over 2. So here we can see that 1 over 2 is less than 1. So by the p-series test, we know that the series diverges. So the only way that a p-series is going to converge is if this exponent is strictly greater than 1 and 1/2 is less than 1. So the p-series test tells me my series diverges. So now let's take a look at this second example. I have the sum of n equals 1 to infinity of 2 over, and I can rewrite this is the square root of n cubed, so this is n to the third power, and the square root becomes to the 1 over 2. So just to kind of show all that additional work here, I am going to rewrite it so that it's 2 over n to the 3 over 2. So now I know that 3 over 2 is greater than 1. So by the p-series test, which I'm going to abbreviate as this from now on, we know that the series converges. Now, if you had a question about this too, we need to remember that in an infinite series that I can pull out any constant. So technically I could have thought of this as 2 times the sum of n equals 1 to infinity of 1 over n to the 3 over 2. And so because this series converges to some finite number, well, I can multiply that finite number by 2 and still arrive at a finite number. So we know that the infinite series does converge. Alright, taking a look at another pretty easy example, I have a perfect p-series form. So all I have to do is recognize here that this exponent, 0.01, that's 1/10. That's definitely less than 1. So I know by the p-series test that the original series diverges. And now finally we're going to get to an example where I'd have to do a little bit more work to make this look like a p-series. So here I'm going to rewrite this as the sum of n equals 1 to infinity. The numerator can be rewritten as n to the 1 over 4, and the denominator is just n squared. So my p-series test says that I want all of my n's to be in the denominator. I just want a 1 in the numerator, or a constant at the least. So what I'm going to do is bring n to the 1 over 4 to the denominator, which would make the exponent there negative. And then my properties of exponents tell me that I would add these two exponents together. So this would be the sum of n equals 1 to infinity of 1 over n to the 7 over 4. So 2 is 8 over 4, and so 8 over 4 plus negative 1 over 4 is positive 7 over 4. 7 over 4 is greater than 1, so 7 over 4 is greater than 1. So by the p-series test, I know that this series converges. Alright, so in this last example I have the sum from n equals 8 to infinity of 4 over n to the fifth. And if I see this general term here, I should definitely think a p-series test. And judging off of the general term and the fact that 5 is definitely greater than 1, this p-series is going to converge. But this starting index here is n equals 8, not n equals 1, which is what the formal p-series test tells us. My question is, does that really matter? So we know that if the starting index is 1, so let's cross this out and make it 1, that if the starting index is 1, then yes, this infinite series definitely does converge by the p-series test. So let's write out a few terms from that particular infinite series. So starting at 1, it'd be 4 over 1 to the fifth, plus 4 over 2 to the fifth, and so on. And I'll go ahead and actually include 4 over 8 to the fifth, 4 over 9 to the fifth, and so on and so forth. So by the p-series test, this infinite series definitely converges. And let's remind ourselves of what that means. That I can add up all of these terms, all infinitely many of these terms, and still get a finite number. So it should stand to reason that if I take out the first 7 terms, so I'll go ahead and put 4 over 7 to the fifth right here. If I take out the first 7 terms here, that the remaining terms are still going to add up to a finite number because I reduced the amount of terms that I was adding together. So the idea with convergence, it's all about at the end. What happens at the end of the series? That's going to tell us whether or not the infinite series converges or diverges. I can go ahead and add 1 billion right here in the front if I really want to. But as long as the numbers at the tail end are going to sum to a finite number, it doesn't matter if I add 1 billion, because that finite number plus 1 billion is still a finite number. So it doesn't matter that my starting index here is an 8. That doesn't affect anything. So I can go back to having a starting index of 8 and still apply the p-series test to determine whether the infinite series converges or diverges. So since 5 is greater than 1, by the p-series test, I have that this infinite series converges. Now the difference is that the infinite series would not converge to the same value with a different starting index, but that wasn't the question. The question was just convergence or divergence. And in general, we can't find what an infinite series converges to anyways unless it's telescoping or geometric. So that's the main idea behind whether or not the starting index is n equals 1 or n equals a million for that matter. We really only are concerned with whether the tail end of the infinite series is able to be added all together to arrive at a finite number.